Okay, the next thing we want to do is come up with the design constraints that our system uses to determine how to draw a crystal. In other words, what are the building blocks of every crystal? What traits do they have in common? To do that, let's look at the original source. This is a picture I took of that brochure that Ruth Lynn made. And we're looking for common qualities. And the first thing that comes to mind for me is that this grid is nice and evenly spaced, which means these are probably all the same overall dimension. So in some cases like these two, they look a little further apart, but if you think of this as a circle, then really they're all equidistant from one another. They're the same size. So when you're sharing a quality across our system, we can think of that as a variable. Why don't we create one? Let's call it crystal size and set it to 500. All right, the other thing that I'm noticing is a lot of sixes. There's a hexagon. These shapes, there's 6 of those, 6 lines, 6 dotted lines. And I think that we can safely assume that all of these are 6-sided elements. In some cases like this one, we have 12 lines, but really that's just doubling the base number of 6. Everything is a factor of 6 and is usually straight up 6. So why don't we just make it easy on ourselves and call a new variable, make a new variable and call it sides and set it equal to 6. Great. Let's see if we can use this to create. I think what would be nice is to know, as we're creating all these fancy shapes and layers and things, to know that they're lining up with the angle that we expect them to be at, and that they are within that limitation of size that we have set. So what I'd like to do is create some test lines so that no matter what we do as we move on, we are within the design constraints that we have set for ourselves. So that means drawing a circumference circle and 6 lines. I'm just going to clean this up a little bit. I don't think we need a background. We don't need that red rectangle. Let's just show you what we're doing as we do it. Let's get rid of this rotation. We don't really need that. And let's draw an ellipse that will act as the outer limit of our shape so that we know if we're going too far or not far enough. Great. Okay, we won't know if we're too far if we're right up against the edge because we won't see it. So let's give ourselves some space here. I'm just making this up. Great. We got to see what's inside of there. So let's say no fill and give it a stroke instead. Great. So now anything we draw, if it's inside of this ellipse, we're safe. If it's supposed to be at its outer limits, we'll know that if it's on the line or not. And if it's outside of this, then we've gone too far. So that's a good test line to have. The next thing we want to do is create those lines, those 6 lines that let us know that we're where we think we are when we rotate around here. So why don't we start super simple, not overcomplicate things. Let's just draw a line. So how would we draw this line? Remember, the origin is right here. We're at 0, 0. So we could draw a line from here to the edge of the circle and then rotate and do another one and just do that 6 times. That's what we'd like to do. So how do we draw 1? Well, as we said, we're at 0, 0. And because the x-axis is here, and we'll discover that it's slightly different than what we expect. But really, let's think of it as just the x-axis in one direction. So we would start at 0, 0, and then the other end of that line is at x amount and 0y. So the point is that we need to figure out what this location is. Now you might think, well, I have to go look up the formula for determining where a point is on the circumference of a circle. And you would be right, except that you're forgetting that we can use this lovely thing called translate, push pop, rotate. That's not a thing, it's a combo, but you know what I mean. We can use this to our advantage. So let's say we're here and we've decided that we're going to draw that line from 0, 0 to x0, whatever that is, and that's equal to the radius of our thing. So the next point, let's say, is down here. We could calculate that as the point on a circumference of a circle, or we just rotate there and we do the same thing again, and then we rotate to our next point and do it there. This is the beauty of using translate and rotate inside of a push-pop combo. So the line function takes 2 points. We have a starting point at 0, 0. Why don't we try to make a line that goes straight down? That would mean no movement in the x direction and a radius movement in the y direction, or half of our diameter, so crystal size divided by 2. Let's refresh that. Great, that's what we want. You could also reverse these. You could go a radius worth of pixels in the x direction and 0 in the y direction, and you have that. And you would start there and it would make a slightly different shape. Up to you. Why don't we go back to where we were, and maybe we can try this again and show you the difference later. So the point is that we have 2 points. We've drawn from one to the other, and now we want to do that 5 more times. And if we're going to repeat something over and over again, that is a good sign that you need a for loop. If you're not familiar with these, take a break, go check out what for loops are, come back, welcome back. We need however many sides we have worth of stuff to do. That stuff is drawing lines, so let's throw it in the loop and let's draw it. Oh, well, we're forgetting something. We're drawing 6 lines. They're all there, believe me, but we haven't rotated yet, so we can't see them. They're all being drawn on top of each other. So let's rotate whatever 360 divided by the number of sides is. Voila. So what's great about using variables like this is if we make one change up here and change sides to 10, we get 10 spokes. And our loop works and everything else works. We don't want 10 though, we want 6. Why don't I show you what it looks like if we switch these around again, which I'm going to do later. So it starts off in a different place, and some of the crystals have that shape, or this orientation. Some of them have the previous one. It's kind of up to you, whatever you want to do. Like, we're not going to do them all exactly the way that Ruth Lynn has done them. But this gets us close enough for now. So that's all good. So we've created a loop. We've done our rotation. Why don't we add some color in here? So there's 2 colors that we know of. There's a pink and a dark blue. And I'm just going to create a variable up here called palette. I want it to be accessible to all of our crystals, so I'm making it a global variable. I'm going to make it an array so that we can access it pretty easily and do all kinds of things with it. And you could initialize it up here theoretically, but P5 throws errors when I do that. And so I had to do it in setup. I only need to do it once, so that's why I'm putting it here. And these are the color values I found that matched what I wanted. So now we can use these. We can get rid of this stroke. And why not just before the ellipse? We'll say stroke palette 0. And then why don't we do the same thing right before we do lines, but change it to palette 1 so we can see both colors. Assignment to constant variable. Ah, yes, let is what we want here because palette is at first an empty array, and then we're going to fill it. So it's not a constant. Great. We have our blue spokes. We have our pink outline. That's all looking very good. I think that one other improvement I'd like to make is to make this a variable, just because I think that's a little bit better in case we want to use that angle for anything else later. Let's see if that works. Okay, good. We didn't break it. Good. So we have this really nice functionality. This does one thing really well. That sentence right there should set off an alarm in your head. That means we should make this its own function. So why don't we call it test lines? We'll give it some space, and we'll just copy everything we've done. We'll just move it. We're not even going to copy it. We're just going to move it. And then we call the function up here. So when we get to draw, it's going to call the function, do all this stuff, reach the end of draw, and because we have no loop, it'll stop. What we expect to see is absolutely no change. Refresh, and we have no change. That is wonderful. So we've created this function. The function draws the design constraints we have, and this will allow us to check all of the new things we're going to draw, making sure that they conform to our design constraints.